Hello, this is part 2 for chapter 2 modulation AM. Okay, so in this part we will learn about power in modulation. Okay, all right, it is I would not say it is difficult, but if we see in a simpler way, you guys should understand on how to find the power. Okay, so power develop when carrier signal appears across resistance R. So this is your equation for power for carrier. PC is equal to EC square over 2R. You don't need to memorize the above part because all the information needed is available in this equation instead. EC square over 2R, where EC is peak carrier voltage. Okay, this is peak carrier voltage, and R is the resistance. Alright, here is the power in AM. So AM signal is a composite of the carrier and sideband signal voltage, and total transmitted power PT is the sum of the carrier PC and the power of two sideband, P upper sideband and P lower sideband. Okay, it is simple to find the power total because it is the sum for power in carrier, the power in upper sideband, and the power in lower sideband, where this is the equation you would use to find each of these. Okay, PC, this is the equation found above, is equal to EC square over 2R, and PUSB and PLSB have similar equations where PUSB is equal to voltage in upper sideband squared over 2R, where PLSB is voltage in lower sideband squared over 2R. So it should be easy to memorize power in upper sideband and power in lower sideband. Okay, so the power in sidebands, it can be found where by using this equation P equals to voltage in lower sideband squared over 2R, and LSB is equal to MEC index voltage carrier over 2. All right, and both of these are squared, where M squared times with voltage squared over 4 times 2R. Where is this 4 coming from? It is from here, where 2 squared will be equal to 4 brought down, multiply the 2R. Okay, and then both of these can be separated, where M squared times 4 over 4 times with voltage carrier squared over 2R, and with this equation is for PC, EC square over 2R. As you can see here, EC square over 2R, just replace this one into PC, so you will get both power in lower sideband and power in upper sideband equals to modulation index squared over 4 times with power in carrier. So if the question only give the value for EC and resistance, for example, you would only need to find PC. Okay, it's when the question gives the value for voltage and the value for resistance, you can use that value to find the power in carrier. And using that same power carrier, you can find both PLSB and PUSB by multiplying the power carrier with modulation index square over 4. Okay, so with the PT over here, since we already have PC, PUSB here, you can use this equation instead. M squared over 4 PC, same goes for PLSB. So this is the sum for PT. Okay, PT is equal to PAM, it's the same thing, no need to worry about both of these terms, equals to PC times 1 plus M squared over 2. Okay, so AM in power efficiency. In AM, information is carried by the sidebands. However, the maximum modulation, the sideband power is at most 33% of the total transmitted power, which means that 67% of the power is wasted in the carrier. To maximize the efficiency of AM, we need to suppress the carrier and eliminate one of the sidebands. Okay, so this is how you would draw the sketch the frequency spectrum for power, where Fc uh, has the same position with power carrier, while the power in upper sidebands is this value. Since upper sideband is equal to lower sidebands in terms of power value, the equation here is the same. Okay, but for frequency in lower sideband and upper sidebands, it is a different value, where Fc plus Fm, while the lower sideband is Fc minus Fm. This one cannot be the same because, logically speaking, F upper sideband should be bigger than F lower sideband. Okay. Alright, this is the transmission efficiency new for AM. Okay, it is where power in sidebands is divided with power total multiplied by 100%. It is to find the efficiency of the power for AM modulation, where power sideband is just power in upper sidebands is added with power lower sideband. Only these two. PC is not included in this equation. Yeah. So if the we carry from the above equation just now, if EC and R is given, you can find PC, and with PC you can find power sideband with this equation. Okay, and then that is your PT when you add all of those together. For power sideband, you just add PUSB and PLSB together in the same question. So it should be easy, where PUSB, PLSB over PT. So if M is equal to 1, where PSB and PT has the same value, it has 100% modulation, and the average power of PSB is equal to 50%, while PC is equal to PC divided by 2. The transmission efficiency becomes N equal to M squared over 2 plus M squared times 100%. And it is equal to 33%, which is mentioned in the above theory, where, however, at maximum modulation, the sideband power is at most 33%. It cannot be exceeding 33%, okay? Even though both of them, if M is equal to 1, it cannot be more than 33.33%, okay? So the AM power efficiency problems is where information are contained in the sideband, not in the carrier, but the carrier signal occupies 60% of the power. Most of the power is wasted on the carrier signals. Also, the upper and lower sidebands are mirror images of each other, carries exactly the same information. So how do we solve this problem? We will remove the carrier and or suppress the carrier AM system and remove one of the sidebands. Okay, all right, for double sideband full carrier, DSBSC contains upper sidebands, lower sidebands, and carrier, and this is most widely used in type of AM modulation. In fact, all radio channels in this AM band use this type of modulation. If we use double sideband suppressed carrier, as you can see on the above, we suppress the carrier. It contains only USB and LSB, and a circuit that produces DSB-SC is a balanced modulator. If we remove the other sideband, it is called a single sideband, SSB. In this modulation, only half of the signal of the DSB-SC is used. Okay, half of this is used, and it contains either lower sideband or the upper sideband, and produce efficient system in terms of power consumption and battery. So in this single sideband modulation over here, it is a power saving solution for uh, sending information. Okay. And vestigial sideband VSB, this is a modulation of SSB to ease the generation and reception of the signal. Okay.